Lecture 6-2, Fourier Transform of Non-Energy Signals. The objectives of today's lecture are to describe when it is appropriate to use Fourier transforms on non-energy signals and to demonstrate finding the Fourier transform of a non-energy signal. Recall that energy signals have energy that is between 0 and infinity, and that only certain non-energy signals have Fourier transforms. Therefore, we must be careful when finding Fourier transforms of non-energy signals. Sometimes it's better to use properties than to try to use the integral, but we will see that. Let's look at a couple of examples. Example 1, find the inverse Fourier transform of x of j omega equals 1. First, we'll try to do this using the integral, and what we get is that x of t is equal to the inverse Fourier transform of 1, which equals the integral from minus infinity to infinity 1 e to the j omega t dt. d omega over 2 pi. We can immediately see that this is going to grow without bound if you try to integrate from minus infinity to infinity. So another way to do the problem is to try it with limits, which equals the limit as w1 goes to infinity and as w2 goes to infinity of the integral from w1 to w2 of e to the j omega t d omega over 2 pi, which equals the limit as w1 goes to infinity and w2 goes to infinity of 1 over j 2 pi t e to the j omega t evaluated from w1 to w2, which equals e to the j w2t minus e to the negative j w1t divided by j 2 pi t. So since e to the j w2t and e to the j negative j w1t are both complex exponentials, as w1 goes to infinity or w2 goes to infinity, it will only rotate, but it will never converge. So we need to find another method in order to solve this problem. And the way we're going to do this is we're going to let w equal w1, which equals w2. And I can now write this equation as the limit as w goes to infinity of e to the j wt minus e to the negative j wt divided by j 2 pi t. And this equals the limit as w goes to infinity of the sine of wt over pi t. And now we're going to write this as a sinc, and we'll have the limit as w goes to infinity of w over pi sinc of w over pi t. So first we're going to sketch the sinc. So here we have our sinc function, and the amplitude is w over pi at 0, and the zero crossings are at pi over w, 2 pi over w, 3 pi over w, or the other direction, negative pi over w, negative 2 pi over w, and so on. So then we want to see what happens as w goes to infinity. So what you should see here is that as w goes to infinity, all of these zero crossings get really, really small, and they're all going to start converging on that center axis right at the origin. So as w goes to infinity, this becomes delta of t right at the origin. And remember, the integral under delta of t is going to be 1. So we are going to prove that the area under the sinc is actually a 1 in order to show for sure that the inverse Fourier transform of 1 is delta of t. There is an alternate method to solve this problem, and it is to use properties. So if I was to solve this problem with properties, I would have that I know that 1 has a Fourier transform of 2 pi delta of omega. So 2 pi delta of t, using my duality property, would have 2 pi evaluated omega, negative omega, but there isn't any negative omega. So I got that by using duality. And then I would divide both sides by 2 pi, and I would get that the Fourier transform of delta of t is 1, which is what we have here. Example 2. Find the Fourier transform of x of t equals e to the j omega naught t. So in order to solve for the Fourier transform, x of j omega is equal to the integral from minus infinity to infinity, e to the j omega naught t, e to the negative j omega t, dt, which is equal to the integral from minus infinity to infinity, e to the negative j quantity omega minus omega naught t dt. And just like with example 1, you can immediately see that it is not possible to take the integral. So what you would do is try to do it with limits again. So instead, I'm going to define the limits of integration as t1 and t2. So I'm going to take the limit as t1 approaches infinity and t2 approaches infinity of the integral from t1 to t2 e to the negative j omega minus omega naught t dt, which equals negative e to the negative j omega minus omega naught t divided by j times omega minus omega naught evaluated from t1 to t2, which equals the limit as t1 approaches infinity and t2 approaches infinity of e to the negative j omega minus omega naught t2 minus e to the j omega minus omega naught t1 divided by negative j omega minus omega naught. So we're going to do two substitutions in the next step. I'm going to let t equal t1 and t2. And I'm going to distribute the minus sign. So this becomes the limit as t approaches infinity of e to the j omega minus omega naught t minus e to the negative j omega minus omega naught t divided by j times omega minus omega naught. And using algebra, this simplifies to the limit as t approaches infinity of 2t sinc of omega minus omega naught t over pi. So here, if I sketch a sinc, at omega naught with an amplitude of 2t and the zero crossings, the first one would be omega naught plus pi over t. The next one would be omega naught plus 2 pi over t, and so on. The zero crossing over here would be omega naught minus pi over t, and so on. And then as the limit as t goes to infinity means that this becomes narrower and narrower. So as t approaches infinity, I end up with an impulse at omega naught, but the area under the impulse is 2 pi. So what we have found is that the Fourier transform of e to the j omega naught t is 2 pi delta of omega minus omega naught. The only thing left for me to prove in order to confirm this is true is that the area under this sinc is indeed 2 pi, which we will do in example 3. The alternate method for solving this problem, which is probably a lot simpler, is just to use properties. So if I was to do this problem with properties, what I would start with is I have a 1 that has a frequency shift in the time domain. And I know it has a frequency shift in the time domain because when you multiply by an exponential, that represents a frequency shift. So in my time domain, I would have this. So since the Fourier transform of 1 is 2 pi delta of omega, the Fourier transform of e to the j omega naught t would be 2 pi delta of omega minus omega naught. Example 3. Now let's examine the relationship between the sinc function and the impulse function. And what we're going to do is verify our result to example 1 by finding the area under the sinc function and confirming that it is indeed 1 so that we can say that the sinc function is converging to the impulse. Okay, so first let's create our sketch again. Recall we had a sinc function with an amplitude of w over pi at the origin, and that the zero crossings were pi over w, 2 pi over w, negative pi over w, negative 2 pi over w, and the limit as w approaches infinity became an impulse function at the origin that has an area underneath of 1. So we're going to find the area under the sinc, which is going to be equal to the integral from minus infinity to infinity of w over pi, the sinc of w over pi t dt, which equals the integral from minus infinity to infinity of w over pi, the sinc of w over pi t, e to the negative j0 dt. Now what you should see here is that this expression in the integral actually looks like a Fourier transform except omega is equal to 0. So we can rewrite this as the Fourier transform of w over pi, sinc of w over pi t, evaluated at omega equal to 0. So what we get is that the Fourier transform is w over pi times the quantity pi over w rect of omega times pi over w divided by 2 pi. So remember, when you have a sinc, the Fourier transform is a rect, and this is evaluated at omega equal to 0. There's only one omega, and that's here. And what you get is that the value is a 1. So we have shown that the area under the curve is a 1 for the sinc function, so it does converge on an impulse. So the last point to make is we now have a new rule we can use, is that if you want the average value for a function in the time domain, you can find that by finding the Fourier transform of that function and evaluating it at omega equals 0. So to summarize what we just said, that if I integrate a function from minus infinity to infinity, x of t dt, which is the area under the curve, I can also find it by finding the Fourier transform of x of t and evaluating it at omega equal to 0. So now let's prove this again for example 2. So what we had in example 2 is we had a shifted sinc function. So it was a sinc function centered at omega naught with an amplitude of 2t, and the crossings for this was omega naught plus pi over t, omega naught plus 2 pi over t, and over here this one was omega naught minus pi over t, and so on. And the limit as t approaches infinity would become a shifted impulse at omega naught, and the area under that impulse would be 2 pi. So this would be 2 pi omega minus omega naught. So now we're going to prove that this is indeed true. It's going to look very similar to what we just did for the previous sinc function. So the area is going to equal the integral from minus infinity to infinity of 2t sinc of omega minus omega naught t over pi d omega, which we can rewrite as 2 pi, the integral from minus infinity to infinity, 2t sinc of omega minus omega naught t over pi d omega over 2 pi, and that's also going to be multiplied by e to the j0, and then d omega over 2 pi. So what you should see here is that this has the form of an inverse Fourier transform where t is equal to 0, because e to the j0, which is really just 1, means that we've evaluated at t equals 0. So I can rewrite this as 2 pi, the inverse Fourier transform of 2t sinc of omega minus omega naught t over pi evaluated at t equals 0. So the inverse Fourier transform of 2t sinc omega minus omega naught t over pi is going to be 2 pi times the quantity e to the j omega naught t. It's a rect again, so it's going to be a rect of t over 2t evaluated at t equals 0, which equals 2 pi. So once again, we've shown that the area under the curve for this sinc function is indeed 2 pi. Example 4. Let x of j omega equal e to the negative alpha, the absolute value of omega, and solve for x of t. So the first thing we'll do is we'll make a sketch of what this looks like. It's a double-sided exponential. So we have x of j omega along the omega axis. The peak is at 1, and then it exponentially dies off in both directions, where the equation of this curve is e to the negative alpha omega, and the equation for this curve is e to the alpha omega. So x of t is equal to the integral from minus infinity to infinity, e to the negative alpha, absolute value of omega, e to the j omega t, d omega over 2 pi. And since we have two different functions, we can split this into two integrals. So we have an integral from minus infinity to 0 of e to the alpha plus jt omega d omega over 2 pi, plus the integral from 0 to infinity e to the negative alpha plus jt omega d omega over 2 pi. So solving this, we get this is equal to 1 over 2 pi times alpha plus jt times e to the alpha plus jt omega evaluated from minus infinity to 0 plus 1 over 2 pi times the quantity negative alpha plus jt times e raised to the negative alpha plus jt times omega evaluated from 0 to infinity, which equals 1 over 2 pi times alpha plus jt plus 1 over 2 pi times alpha minus jt, which equals to, after simplification, 2 alpha over 2 pi times alpha squared plus t squared, which equals alpha over pi divided by alpha squared plus t squared. So now let's create a sketch of x of t. So the sketch of x of t has the following shape. At 0, it has a value of 1 over alpha pi, and then it dies off this direction and dies off this direction. We're at the halfway point where t is equal to negative alpha and positive alpha. It has a value of 1 over 2 alpha pi. So this concludes the answer to the original question, but now we want to show that you can actually use this as an auxiliary function in order to find the inverse Fourier transform of 1 again, which was example 1 in this lecture. So for the next half of this question, what we're going to do is we're going to find the inverse Fourier transform of 1 again by using another technique. And the way we're going to do this is we're going to let alpha go to 0. So if we let alpha go to 0 for x of t, what we'll see here is that this middle term will start to blow up and go to infinity, and at alpha and negative alpha, they will become closer and closer together, going towards the origin. So it's going to start to look like this. And in the frequency domain, as alpha goes to 0, for x of j omega, which we sketched at the beginning of this problem, it's going to start to look like this. The center is going to still be at 1, but now the dying off is going to become slower and slower. So it takes on that shape. So eventually, if you think about alpha equal to 0, what you see is that x of t becomes the impulse function delta of t. And in the frequency domain, as alpha approaches 0, x of j omega flattens out and becomes a 1. So once again, we've shown that the Fourier transform of delta of t is a 1. There's only one verification left in order to make sure this is true, and it's that we have to show that the area under x of t is indeed 1 because the area under the impulse function is 1. So the area is equal to the integral from negative infinity to infinity of x of t dt, which equals the integral from minus infinity to infinity of x of t e to the negative j0t dt, which translates into x of j0, which is the Fourier transform evaluated at 0. And we know the Fourier transform because we were given that at in the original problem statement, and we know that that's at the origin, and it does have a value of 1, which means that the area under x of t is 1. And as we said in the previous problem, this also represents the average value of x of t. Example 5. Use the following energy signal x of t to find the Fourier transform of the signum function. So we will define x of t to be our auxiliary function for this problem. So the first thing I'm going to do is to sketch x of t. So here we have x of t, which for t greater than 0 is e to the minus at. And for t less than 0, it is negative e to the at, where the value here is 1 and the value here is negative 1. So first, what you should see here is that as a goes to 0, x of t will take on the shape of a signum. So if we can find x of j omega and let a go to 0, then we can find the Fourier transform of the signum. So first, for the energy signal, x of j omega is equal to negative the integral from infinity to 0, e to the at, e to negative j omega t dt, plus the integral from 0 to infinity e to the minus at, e to the negative j omega t dt, which equals negative the integral from negative infinity to 0 of e to the a minus j omega t dt, plus the integral from 0 to infinity e to the negative quantity a plus j omega t dt, which equals negative 1 over a minus j omega plus 1 over a plus j omega. Collecting like terms and simplifying, this becomes 2 omega over j times a squared plus omega squared. So now, to find x of j omega for the signum, we let a go to 0. And what we have is that x of j omega is equal to a piecewise function. It's going to be 2 over j omega for omega not equal to 0, and 0 when omega is equal to 0. So now the question becomes, how did I know that this was the value when omega is equal to 0? Where it's based once again on finding the average value. So remember, if I could find the average value, I have a signum function here. So the area from negative infinity to infinity of a signum function is going to equal 0. That's the average value or area under the curve. And since this also translates into the value of the Fourier transfer function, the Fourier transform at omega equals 0, I know that x of j omega must be 0 when omega is equal to 0. Example 6. Find the Fourier transform of the unit step function u of t. So once again, we could use an auxiliary function in order to solve this problem. We could use e to the minus at u of t, very similar to what we did in the prior example, or we could just use what we already know. So u of t has the following shape. It's a step function that is 0 up to time 0, and then it's a 1. So since we just solved the signum problem, what we can do is write u of t in terms of a signum, and we know that u of t is going to be equal to 1/2, which is a constant over all time, plus 1/2 signum of t. So then when we find the Fourier transform of u of t, we just need to find the Fourier transform of a constant and the Fourier transform of 1/2 the Fourier transform of signum of t. So it's going to be 1/2 times 2 pi delta of omega plus 1/2 times 2 over j omega, which simplifies to pi delta omega plus 1 over j omega. And so once again, note that we have an impulse when omega is equal to 0, where the area under it is equal to pi. So that is important. So we have found that the Fourier transform of u of t is pi delta of omega plus 1 over j omega. And this concludes lecture 6-2 on non-energy signals.